Alrighty, hello everyone, and we're back. Going over 2022 AMC 10B number 1 through 10 on this video. And as promised, I will release these video solutions really quickly. So about 3 days per episode, and I will do that until we finish this test. Well, not exactly 3 days, because the fact that a week 7 days is a prime kind of makes it hard to make the upload schedule. So I am thinking tentatively a new episode every Monday and Thursday. But with that being said, we can get started with number 1 first. Number 1, it says, define x diamond y to be the absolute value of x minus y for all real numbers x and y. What is the value of that expression? So we can just calculate, okay, let's see, the value of 2 diamond 3, that looks like 2 minus 3 absolute value, so that's a 1. 1 minus 1 absolute value, so that is 0. Okay, let's take a look at the right hand side. 1 minus 2 absolute value, that's 1. 1 minus 3 absolute value, that's 2. So our final answer is 0 minus 2. No absolute value at the end, so that is negative 2. Don't choose 2. The answer is A, negative 2. Alright, number 2. Number 2, it says, in rhombus ABCD, point P lies on segment AD so that BP is perpendicular to AD. Given that AP equals 3, PD equals 2, what is the area of the rhombus ABCD? We're given that it is a rhombus, so AB and AD should have the same side length, correct? So AB should have a side length of 3 plus 2, or 5. And by the Pythagorean theorem, we know that BP is going to have a side length of square root of 5 squared minus 3 squared, which is 4. 3, 4, 5 triangle, right? So the area is just base times height. You don't know the area, that's fine. We can see, okay, let's take this triangle over here. Because this is a right angle, we can move this over here. That becomes a rectangle with height 4 and width 5. So the area is just 4 times 5, or 20. That's number 2. Alright, moving on to number 3. Number 3 says, how many 3-digit positive integers have an odd number of even digits? Kind of confusing, but we want to find 3-digit positive integers such there are 1 even number or 3 even numbers, or even digits. So if we have 3 even digits, then all we can have is 0, 2, 4, 6, 8. That is 3 even digits. The first digit cannot be 0, so that's 4 possibilities, times 5 for the second digit, times 5 for the third. If we have, that is for the case of 3 evens. For the case of just 1 even, then we have this 0, 2, 4, 6, 8 to choose, but then we have 2 odd digits, which we have to choose from 1, 3, 5, 7, 9. If that even digit is in the first place, then we only have 4 possibilities. And 2 odd digits, we would have 5 times 5 possibilities. If, however, the second digit is even, then, now it has 5 possibilities because it now can have 0. So that's 5 times 5 times 5. And the last is also 5 times 5 times 5. The underlined digit is going to be even. Okay, now we add those up. You might have noticed that I did not find these products initially. That is because we can kind of calculate this first just to simplify our expression just a little bit. Even though you might just, it's gonna save like 5 seconds. So if you calculate it, it's not a big deal. But we just get 18 times 25. You don't have to really calculate this. Divide that by 2, we get 9 times 2. Divide that by 5, we get 5 times 5. So it is 45 times 2 times 5, which is just adding a 0 at the end. So our answer is going to be answer choice D. All right, number 4. Number 4, it says, a donkey suffers an attack of hiccups. The first hiccup happens at 4 one afternoon. Suppose that the donkey hiccups regularly every 5 seconds. At what time is the donkey's 700th hiccup occur? Okay, let's think about this. So we have 4 o'clock, right? And we want to add 5 seconds afterwards every single time until the 700th hiccup. Okay, let's think. So the first hiccup happens at exactly 4 o'clock and 00 seconds, I guess. And, okay. And we have 5 seconds after that. How many 5 seconds does it occur for the 700th hiccup to occur? So let's think. If the hiccups are like these, and the time intervals between them are 5 seconds. If you note, if we have one 5-second interval, 2 hiccups in total occurs. If we have 2 of them, then 3 occurs. If I have 3 of them, then 4 occurs. If I have 4 of them, then 5 occurs. Okay, so if I have 700 hiccups, then we have 699 of those intervals, of 5-second intervals. So it is going to be 699 times 5 seconds. That is going to be easily to calculate it, 700 minus 1 times 5, which is 3500 minus 1. And we just now have to figure out, well, how much time it takes. We can say, okay, it's probably 58 minutes. So 60 times 58, again, you don't have to calculate it. Well, you do, but like it's an easier way to calculate it if you just say 60 times 60 minus 60 times 2, or 120. 3600 minus 120, that is going to be 3480 seconds. And we have 3499 seconds, which means that it is going to be, or minus 5, excuse me. Then it is going to be 3495, or 15 seconds, or 15 seconds after 4:58. Cool, number 5. So number 5, it asks, what is the value of that expression? Kind of annoying, but first of all, it's kind of hard to factor this out of the square root. So let's just put everything in the square root. 1 plus 1/3 squared, 1 plus 1/5 squared, 1 plus 1/7 squared. At the bottom, we can factor by a difference of squares. That becomes 1 plus 1/3 times 1 minus 1/3, 1 plus 1/5 times 1 minus 1/5, and 1 plus 1/7, 1 plus 1/7 times 1 minus 1/7. Cool. So now we can get rid of some of the common factors. None of these are 0, so we can divide by those numbers safely. So now we have 1 plus 1/3, or 4/3, over 2/3 times 6/5 over 4/5 times 8/7 over 6/7. Note all of that is in the square root. The denominators cancel out, and some of that also cancels out. That leaves you with amazingly square root of 4, which gives you the answer of 2. So it's a kind of a messy problem, but the answer turned out to be nice and neat. All right, number 6. How many of the first 10 numbers in the sequence that are prime numbers? I know it threw a lot of people off, including me during the context as well, because, how are you supposed to find the number of sequences that are prime numbers? Okay, initially I tried, maybe mod 3, the divisible by 3. This is not really divisible by 3. If I add that, that's 4. Okay, this is divisible by 3, but that doesn't help. Now that doesn't I tried a lot of factors, but none of them worked. And then I saw, okay, if I have this 2 over here, that's kind of annoying. Maybe if I can break this up into 1, 1, and 1, 1. So that adds up as a 2 if I just put in the placeholder zeros. Maybe I can factor out this 0. So maybe it becomes 1, 1 times 10 plus 1. Oh yeah, that just proves it's not a prime number. Same thing happens here, 1, 1, 1. So it's 111 times 100 plus 1. Same thing happens with the next number. If we just break it up, get 1,111 times 1,000 plus 1. All of these are not prime numbers. So we have just proven that none of the numbers in the sequence are prime numbers. So yeah, none of the first 10 numbers. That first 10 numbers also threw some people off. They thought, okay, maybe something would be different afterwards. They didn't look for general, fact that all of these numbers can be factored. I'd say rather easily if you see the trick. So the answer is going to be 0. All right, number 7. For how many values of the constant k will the polynomial that have 2 distinct integer roots? So if we have 2 distinct integer roots, let's just factor this to x minus r. I rather write it as x minus r, x minus s. So if we just distribute it, we get x squared minus r plus s x plus rs. So we know that k is equal to negative r plus x s, and that 36 is equal to rs. By the way, that is also where Vieta's formula comes from, if you are curious. Okay, so rs has to be integers, so maybe we factor 36. That is equal to 2 squared times 3 squared. Okay, let's think. How about, let's just make a table of r's and s's. 136. Okay. Because r and s are symmetrical, we don't consider the case where like it's 36 and 1. It will give the same k value. Let's get another column k. 2, 18, 3, 12, 4, 9, 5 doesn't work, 6, 6. Is that it? So the k values that we can calculate negative the sum, so negative 37, negative 20, negative 15, negative 13, negative 12. Is that it? Well, no, because r times s is 36, it's positive, but it doesn't say r and s are both positive, so we can actually get a negative value. When both r and s are negative, then k is going to be positive 37. And they're different, and it asks for how many values of constant k. So, okay, we have negatives of all of those values that we found, which turns out for us to be 10 of them. Okay, now even that is not the correct answer. Let's think, what have we missed in terms of the factors, how many values of the constant k that we can use? Aha! Did you realize what mistake I made? Intentionally, that is 6, 6, or negative 6, negative 6. It asks for 2 distinct integer roots. So that gives you an answer of 8. That is the mistake that I intentionally made, was the reason that I didn't like this question, particularly for its answer choices. It doesn't have 10. Like, people could really silly on that. So, why not put in 10? But if you thought it was 10, kind of the answer choices saved you from one silly mistake. All right. Next problem, number 8. So we want to consider the following 100 sets of 10 elements, each containing all of these numbers, and we want to find how many of these sets contain exactly 2 multiples of 7. I've seen a lot of like bash solutions, but I feel like there is a need for me to address one of the best solutions that I've seen for this problem. It's very clean. So let's think about this. If I have 10 elements in each set, and the farthest 2 multiples of 7 can be is, let's say 7 and 14. That is 8 elements containing 7 and 14. So if we don't want any multiples of 7, we only have 6 elements, consecutive elements. We can't have that. We have 10 elements. So all of these sets contain at least 1 multiple of 7. Now let's think about if I want to have 3 of the multiples of 7, then all of these numbers, let's think, we have 7, 7, 1. We need 15 total elements. Even if we start from a multiple of 7 and end at a multiple of 7, we need 15 elements, but we only have 10 elements. So at most, 2 multiples of 7. So all of these, let's say all of these have either 1 multiples of 7 or 2 multiples of 7. And we want to find how many having 2 multiples of 7. So how many multiples of 7 are there in the first 1,000 positive integers? We can divide 1,000 divided by 7. We want to take the floor value. Just in case, just please list out every arithmetic you do. It really helps to save any silly mistakes that you might make along the way. 140, well, I made a mistake. 2, 14, and 6 remainder. We don't really care about that. 142 of them. And there are 100 sets. Now, if we assume all having 1 multiple of 7, then we only have 100 multiples of 7. But we have 142 of them. So for each set that have 2 multiples of 7, it contributes 1 more than we have already accounted. So there are going to be 142 minus 100, which is exactly 42 sets containing 2 multiples of 7. It's really clean. You don't have to like really casework on like, oh, what 7? I've seen some people like just write out first, let's say 7 sets and like count. Kind of, annoying and also really easy to mess up on. So I feel like this is a clean solution that it's worth sharing here. All right, number 9. It asks the sum that is expressed as a minus 1 over b factorial, where a and b are positive integers. What is a plus b? So all of these numerators are exactly 1 less than the denominator. So maybe you think, okay, something has to work out properly, so we like cancel a lot of these terms. So because all of these are 1 less, maybe let's try 1 over 2 factorial plus, let's just make it exactly 3 over 3 factorial, but subtract that 1 out. So this is equivalent to 2 over 3 factorial. Plus 3 over 4 factorial, that we change that to 4 over 4 factorial minus 1 over 4 factorial plus ... plus 2022 over 2022 factorial minus 1 over 2022 factorial. You notice that here that collapses into, because 3 factorial divided by 3 is just 2 factorial. So that just collapses into 2 factorial, 1 over 2 factorial minus 1 over 3 factorial plus 1 over 3 factorial. That collapses into that minus 1 over 4 factorial plus ... plus 20 or plus 1 over 2021 factorial minus 1 over 2022 factorial. This cancels out with that, this cancels out with that, and this cancels out with the term before it. So now we just have 1 over 2 factorial, just 1 over 2, plus 1 over 2, minus 1 over 2022 factorial, or 1 minus 1 over 2022 factorial. And our answer is in the form of a minus 1 over b factorial. So we have a equals 1, b equals 2022. So our answer is going to be 2023. Answer choice D. All right, number 10. Number 10, it says, Camilla writes down 5 positive integers. The unique mode of these integers 2 greater than their median, and the median is 2 greater than their arithmetic mean. What is the least possible value for the mode? Okay, so it says the unique mode of the 2 integers is 2 greater than their median. So the median has to lie here if this list of integers is sorted in ascending order. Then the unique mode is 2 greater than that. Okay, I have to have a unique mode, so I have to have at least 2 numbers, and it is greater than the median, so these 2 have to be the same, has to be the mode. So if the median is x, then these 2 has to be x plus 2. Okay, next. And the median is 2 greater than the arithmetic mean. So the arithmetic mean is equal to x minus 2. What is the least possible value of the mode? We want to find the least possible value of that. So the sum of all elements, or sometimes denoted as sigma. Sigma just means sum of all of the elements, is equal to 5 times the mean, which is 5x minus 10. So now over here, 5x minus 10 minus what we already have, x plus 2 plus x plus 2, always quantity, which is 2x minus 14. Correct? So over here, we have 2x minus 14, and each of these are like x minus 7. But it doesn't work because we remember, it's a unique mode. So these 2 elements over here cannot be the same. So one of them has to be a little bit less, one of them has to be a little bit more. The reason that I put them so close together and not like x minus 13 and x minus 1 is that all of these elements, remember, are positive integers. So we want x to be least possible. So we want this kind of ceiling for this x minus 13. If I have x minus 13 as a positive integer, then what we have over here is going to be x minus 13, let's say, equal to 1, then x is 14, which is really big, which we don't want. So here the best we can do is x minus 8. That becomes the smallest positive integer, which is 1. So then x becomes 9, and that unique mode is going to be x plus 2 or 11. And we can check that our answer 1, 3, 9, 11, 11 actually indeed satisfies the condition that it asked for. So that is it for the first 10 problems of AMC 10B, and I will release more videos on this later down the line, and I will see you later. Peace out.